Hexaflexagon. Hexaflexagon.
What is a hexaflexagon? From Vi Hart's videos, we could come to a simple definition of what we perceive a hexaflexagon to be so far. Let's just say for now that a hexaflexagon is a hexagon figure that folds into and out of itself to make new hexagon figures of the same proportions. We have a general concept of how to make one, so let's do some exploring on our own of how to construct this. We can make some definitions to start off with. Triangle numbers, the numbers of equilateral triangles within a strip of paper. Faces, the number of sides a hexaflexagon has. This determines its name. Di, tri, tetra, penta, hexa, etc. A hexaflexagon is a hexagon figure that folds into and out of itself to make new hexagon figures of the same proportions. The end result is based on the number of equilateral triangles, the number of folds to produce a hexagon figure, the number of faces found via folding the original hexagon figure, and the specific folding capacity for which one cannot find more faces of a particular face. From Vi Hart, we learn, with some exploration on our own, how to construct a tri-hexaflexagon. It is less difficult as we just have the 9 triangles and need to start at the wrapping of every third triangle in our original instructions. This is a tri-hexaflexagon. So now, using our bigger example of a tri-hexaflexagon, we can flip through to show you all the different faces. We have 1, 2, and 3. Could we relate these numbers in a sequence? Relating those two types of triangles to their face value, we have 3 face relating to the next face by an additive of 3 or an additive of 3 times 1. In terms of the triangle on triangle glued, we have a difference of 9 or 3 times 3. Also, for the triangles glued edge to edge is an additive of 9 or an additive of 3 times 3. In terms of relating faces to the triangles glued on top of each other, we have a multiply of 3 to the power of 3 or an additive of 6. Or when comparing 6 to 18, we just have a multiple of 3, so by default it is a multiple of 3. When relating faces to the edges glued together, we have a multiple of 3 plus 2. How many triangles do we have? Does that matter? How many faces do we have? Can we compare those? So within a tri-hexaflexagon, we noted the corners in the middle. You can see they're labeled with 1s. And as we fold, those 1s go from the center on the front side to the outside corners on the back side. You can see that as we continuously flip, it happens with multiple ones. There's 2, and 2 folds out to the outer corners of the back side also. You can also see there's parallelograms that follow each other throughout the entire place. So if we fold, that same parallelogram is going to be represented on the other side together. Interesting. Okay, I wonder if we cut off the corners, would our figure flip into a snowflake pattern, or would it fall apart? We don't want to take our chances here, but if you'd further analyze this later, you are welcome to. Maybe since we just used straight lines before and found only tri and hexaflexagons, maybe we could start out with different templates for those we haven't found yet. We went ahead and we found a 4. So it was this bizarre shape, zigzagging. Came out to be 13 triangles. And as you can see, it will have 4 sides. 1, 2, 3, 4. We then discovered a pentahexaflexagon that had 5 sides. It ended up being this zigzagged figure, less of a zigzag, but more triangles. It had 15 triangles, and as you can see, we have 1, 2, 3, 4, and 5. Awesome. As mentioned before, we're going to look into starting points of hexaflexagons as if they could all be straight lines. Let's look into this. We could probably make them work if we started out with more triangles in a straight line and glued the undersides of the folded triangles together. Let's add a definition. Straight line intermediate families. Those hexaflexagons that can be folded, according to our data so far, starting out from a linear strip of equilateral triangles. We have 3 and 6 that we've already found. So you can see the faces 3 goes to 6 by additive of 3 or the multiplier of 2. Going off of the 3, we can find a 9, which is hypothesized, or a 12, which we found via a credible source to be accurate. Also, if we did not use what we hypothesized, we can still use the multiply of 2 from 3 to 6 and from 6 to 12. That also works proportionally with the number of triangles, where you can add 9 down the row, including our hypothesis of 9 faces, or you can multiply by 2 again to get 9 to 18 and 18 to 36. Adding the definition of straight line extended families, we can include the 4 and the 5-faced hexaflexagons that could be drawn from a straight line but folded and glued to make their zigzag shape. And as you can see, you can make 3, 4, 5, and 6 faces all out of 18 triangles depending on how you fold it.
We already have templates for each hexaflexagon, and we have shown the end results for each of the different faces. Now let's explore how we actually got to the results. Let's flex. Let's start by folding the trihexaflexagon. Then you go over the tetrahexaflexagon. You proceed with folding the pentahexaflexagon, another zigzag pattern to start with. Let's begin folding the hexahexaflexagon. It basically goes into a trihexaflexagon with 9 triangles, but it's overlapping 2-story paper strips made out of 18 triangles. I wonder if the tetra and the penta fall into that same 9 triangle shape.
Let's map a trihexaflexagon. Here's the mapping pattern we found for a trihexaflexagon. So you can see we have our red, which can go to a blue, which can go to a green, which can go back to a red. And as you can see, that's represented within a triangle forming here from red, blue, and green. Okay, for the mapping of a tetrahexaflexagon, the 4-sided hexaflexagon, we have our 4 sides. So then for the pentahexaflexagon, we have the mapping as such. So then for our hexahexaflexagon, you can see the mapping is as such. Again, we have 6 sides for this one. So now we have found and know hexaflexagons exist for faces of 2, 3, 4, 5, and 6. We've related this to both triangles glued on top of each other and triangles glued edge to edge, as such, of multiplier by 3 times 2 and by 3 respectively. We've related the faces also to our mapping triangle results, wherein the faces minus 2 equal the resulting triangles from mapping. We've also related each triangle glued to the next one, wherein we had multiplier of 3 times 3, where that's added between the 11 and 20 and the 9 and 18. And among the glued triangles edge to edge that we analyzed, we had an addition of 3 each time. And then we also have our straight line type, where our default had none, trihexaflexagon had intermediate, tetrahexaflexagon had extended, pentahexaflexagon had extended, and hexahexaflexagon had an intermediate straight line type. fortune teller. We used to make these in elementary school. What is your future?
Pick one.
Try.
T-R-I.
3,
1, 2, 3.
2. Explore more with Hexaflexagons. Woo! Happy flexing.
I got the magic in me. Every time I touch that track, it turns into gold. Everybody knows I got the magic in me. When I hit the floor, the girls come snapping at me. Now everybody